Okay, good morning. Last time, I think we have talked about the polymeric structures, but today we will talk about what kind of polymers that we will be studying. Okay, I think I will introduce about 9 types of polymers. Okay, just in the case of a homopolymer. Okay, we are talking about homopolymer, not copolymer. I will introduce you 9 types of the homopolymers first, and then we'll move on to the copolymer systems. Well, this is the linear polymer and branch polymer and cross-linked polymers. Okay? Name linear polymer says that you have a linear chain, okay, which look very much like this. It's a linear string, but it's not just a rod like a structure, but it could be like a strands or a string. Okay? Branch polymer is the one that you have branches or grafts. Okay? So you have a graft in the linear form. Cross-linked polymer is the one that you form a chemical linkages between the linear chains. Okay? So if I will describe, then linear polymer is the one that you have a linear skeletal atoms where these structural units are attached. Okay? Examples are the ones that we have a polyvinyl chloride, polymethyl methacrylate, polyethylene, nylon, and so on. Okay? Cross-linked polymers are the ones that you have all these chains linked together. Okay? So linear polymer could be stretchable, flexible, and stretchable, whereas branched polymer has grafts, so that when you pack it in the space, density is much smaller here than the linear polymers, okay, if it's given in the space. Cross-linked polymers have a property where it's not stretchable because of the cross-links. It's not stretchable. It's not soluble because when you put this polymer in the solvent, okay, because of the links between the linear chains, it will not be melt or soluble, whereas the linear polymer is soluble in any organic solvents. So the properties are quite different. Okay? You can make a branch polymer or cross-linked polymer from these types of polymers as well. So in other words, in the case of polyethylene, you can make a linear polymer, or you can make a branched polymer, or you can make a cross-linked polymer depending upon how you are making your polymer. Okay? Next, the polymer type that I will introduce is the star polymer. Looks very interesting, right? It looks like a star, and well, it starts from the core, and it will move on to like an arms. Okay, you have many arms, okay? And some of the other types of polymer look something like this or like this. So this is the core or starting point of your polymerization. It will move on to and grow like a star. So depending upon how many arms that you have, you can make different types of stars. We have a dendrimer. Dendrimer is very similar to the star polymer, but you have a growing chain, which is represented as a blue star. Okay, blue points will grow, and it will look like something like this. It's much similar to the star polymer, but it's a little different because you have other types of growing polymers. It's not in this case, this is not a 2-dimensional, but it's a 3-dimensional stars, 3-dimensional polymers. And this one too could be a 3-dimensional. Okay? You have many of the other arms, which is different from this star polymer. Okay? We call this as a dendrimer. Okay? Or we have a ladder polymer. Ladder is very much like a ladder. So you have a linear chain, okay, which was linked between the chain. You have cross links, but it looks like a ladder. Okay? It's a type of the cross-linked polymer, but a little different from the previous, the cross-linked polymers. Okay, let me say 3 more polymers where we have a cyclolinear polymer. Cyclolinear linear polymer, but you have rings. We have cycles, okay, which look something like this. Okay. It's a benzene ring, and you have other substituent groups in between these benzene rings. So we have aromatic ring, and this is a little different from the first linear polymer. It's a linear polymer, but because of the cyclic ring, which is benzene, you have a very strong nature of this polymer. Right? If it's and this is different from the polyethylene. Okay, polyethylene consists of a CH2 and CH2 and so on, but because of the rings or benzene rings, it's very strong. Right? Very difficult to dissolve, and difficult to the melt because of the nature of the benzene, which is very flat, right? And you can pack it very densely. So it's what we call is a cyclolinear polymer. We have a cyclomatrix polymer. Cyclo means that you have a ring, okay? Cyclomatrix ring, which is consisting of the silicon. Silicon is the inorganic the atom, whereas oxygen is organic, and this is what we call the inorganic and organic complex polymer. Right? Most of them are made of carbon, hydrogen, nitrogen, and oxygen. Okay, and in that case, we call that as organic polymer. Whereas if you contain some inorganic part, inorganic atom in your polymeric system, we call that as inorganic polymer or organic inorganic polymer. In this case, we call this as organic inorganic polymer. Silicon, we call this as a siloxane. SiO is a siloxane. This siloxane ring is linked together just like a star, okay? And we call this a cyclomatrix polymer. Lastly, I will introduce you the interpenetrating network, interpenetrating polymer network. Okay? This is the network polymer, which means that you have a cross-linked system, but you have 2 different types of networks. Now, once you form a cross-linked structure, okay, this is the polymer network polymer, whereas second monomer is embedded in and cross-linked together. So you have a two network polymer. Well, this is the first network, and the second network is just like a net, okay? Net. The 2 nets are linked together, and this is one type of the network polymer. But what we call is IPN, interpenetrating polymer network, IPN polymer, and in this IPN structure, we have a full IPN and semi-IPN, and depending upon how you are making. But IPN is a cross-linked polymer, but we have 2 networks gathered together. Okay. So these are the homopolymeric systems. Most of them are homopolymeric systems. But we will talk about the copolymer systems as well. Copolymer is different from homopolymer in terms of the number of the monomeric units that you have. Okay? In the case of copolymer, you have 2 types of monomers. Okay? Well, the homopolymer is the one that you have one monomer is gathering together to make the linear polymer, or star polymer, or the branch polymer, cross-linked polymers. You can make 9 or 10 types of polymers. Whereas in the case of copolymer, you have A monomeric units and B monomeric units. A and B are different monomers. In the case of copolymer, we have at least 4 types of copolymers. Okay? Alternating copolymer is the one that you have A and B are alternating each other. Okay? Once you have A, monomeric units, then next one is B. A, B is alternating. Random copolymer is the one that, well, A and B sequences are randomly copolymerized. Okay? So you don't know, you know, the monomeric units once you form an A or B type of copolymers. Block copolymer is the one that you have an A block. Once you form a certain length of the A block, and then you have a B blocks, okay? A block and B block. So we call this as a block copolymer. Graft copolymer is the one that is like a branch polymer, but you have a, you know, substituent group or side chain. Side chain is different from the backbone linear polymer. Okay? Well, properties are quite different depending upon the type of the copolymers. Okay? A block copolymer is sometimes easy to make, but sometimes very difficult to make, okay? Depending upon how you're making. Block copolymer is different from random copolymer because you know, the property of A block and property of B block is matched together, whereas the random copolymer, the A and B is quite mixed and randomly distributed. So it's more like a A and B combination, whereas the block copolymer, you have a certain property of A and certain property of B, whereas random does not have any, you know, the property of A or B. Okay? For example, we will talk about the glass transition temperature. You know the melting temperature of the copolymer, of the polymer, or of the metal. Okay? Well, if you're talking about the material, most of the material, such as metal will melt. Okay? Once you heat it up. Okay? Once you heat it up, you make the melt. The melting phenomena always occurs when you have crystals. Okay? So metal or ceramic material has a melting point because of the crystallinity. Okay? Whereas polymer, organic polymer, maybe melts or may not, depending upon the crystallinity of your polymeric system. Okay? Once you have crystals in the polymer, then it melts. Okay? If the polymer will not have any crystallinity, okay, then it will not have any the melting points. But before the melting point, we have always a glass transition temperature, which changes from the glassy state to the rubbery states. Okay? We will explain to you, but all the polymer has a glass transition temperature, but the glass transition temperature of A and glass transition temperature of B could be very distinguishable in the case of a block copolymer. So you may have a 2 TG. Once you scan increase your temperature, this block copolymer may have a 2 TGs. But in the case of random copolymer, perhaps you may have a 1 TG, 1 glass transition temperature, because of the A nature and B nature could be very much combined together. Okay. So we will move on to the cross-linked polymeric structures. Cross-linked polymers are the ones that, you know, the polymer chains are linked together, or when polyfunctional instead of difunctional monomers are used. Okay? Polyfunctional means that you have many functionality. Difunctional means that you have 2 functional groups, such as amino acid. Amino acid has 2 functional groups, amine group and carboxylic acid group. Okay, you have 2 functional groups. Whereas polyfunctional means that you have many functional groups. Okay? If you have many functional groups, then you can form the cross-linked structure or the network structures. If you go back to to this case, we call this as divinyl benzene. Okay, this is the styrene monomer. Styrene monomer has 1 double bonds. This double bond could be, you know, could form a radical once you attack your the double bonds. So you have two radicals from one double bonds. Okay? Once you break the double bonds. So that's why we call this as difunctional or bifunctional. Okay? If you have two double bonds, we have four functional groups. So this is regarded as a polyfunctional. Okay? Because of this divinyl benzene, you can make a network structure, something like this. Okay? In this way, you can make the network or cross-linked polymeric structures. So always, the cross-linked polymer has a polyfunctionality. Functionality or functional group could be over, two can form the network polymers. The example is a vulcanized rubber, okay? Rubber or tire, pneumatic tire, could be cross-linked polymers. If it's not cross-linked polymer, it will melt. It doesn't have any viscoelasticity. Okay? Network polymer, because of the cross-linked in nature, we can form the network polymer structures. Vulcanized rubber could be, cross-linked because of the sulfur linkages. Okay? I think I will tell you a little bit more about this vulcanized rubber in the history of polymers. So once you have a polymer chain, then if you cross-link them, we have many advantages. Okay? We have many advantages, or you have different properties depending upon the cross-linked systems. The first advantage of the network polymer is that it will impart the excellent dimensional stability. Dimensional stability. Dimension. Okay. If you heat it up, this film. Okay. Once this is the paper cellulose, but if you heat it up, if you put it in the oven, okay, heat it in the oven, it may shrink or it could expand. Excellent dimensional stability means that it doesn't have any dimensional change once heated up or cooling down. Okay. Okay. If it shrinks very extensively or expands very enormously, then we do not call this as an excellent stability. Okay. In that case, dimensional stability of this material, which shrinks or enlarge, it will not have any excellent stability. It has a bad it has a very weak dimensional stability case. So excellent stability is coming from the network structure. Okay, once heated up, your chain may move. Okay, okay. Melting point is the one that it changes your phase from the solid phase to the liquid phase. Okay, the crystal melts. So if you heat it up, your material, then polymer chain will move. Okay, okay, move very extensively. Because of this, movement, you need much more space to move. Okay, so free volume, your volume, specific volume will increase upon heating. Okay? But once you have a network or cross-link, then you have a restriction of your movement. And because of this restriction of your movement, you have a very excellent dimensional stability in the case of network polymer. Second, characteristic of this cross-linked polymer is that you form the thermoset. Thermoset. Thermoset means that I think I will introduce in the next slide, but thermoset is the one that it will not melt, okay, because of the cross-link. So you can form the thermoset plastic rather than thermoplastic. Right? I will introduce you what does these two things means. But anyway, thermoset polymer will not melt or floor upon heating. So you cannot make the molded system in the case of cross-linked structure. Whereas the thermoplastic will melt. Okay? so you can form the mold structure. Third characteristic is that usually cross-linked polymer will not be soluble, but it will only swells the solvents. Okay? So these are the three very distinct structure of the network polymer. So let's say that what's the difference between the thermoplastic and thermoset? Thermoplastic, usually it will become soft material upon heating. If you heat it up, because of the linearity, you move your polymer chain will move so that it will become very soft material. And at a certain point above the melting temperature, then it will become liquid from solid phase. So it melts and flow because of the liquid structure. It will flow when heat is applied. But you can also the heating will melt, and if you cool down, it becomes solid material. So it's a reversible. Okay? Okay? Phase change will be reversible depending upon your heating and cooling. Whereas in the case of thermoset, just like an egg, okay? Egg, just like an egg, if you heat it up, it will not melt, and it will just break your bond. Okay? Okay? Break your bond. So normally, thermoset is not soluble, as we can, we said just the previous slide, or infusible, and property seems to be quite different depending upon the material. It's very strong. Once you make the network polymer, it becomes very strong and hard, but has a very excellent dimensional stability, and also has a very high heat resistance. Okay? Heat resistance. It will become very strong even at high temperature. You cannot. This is irreversible. Okay, so that you cannot reprocess. You cannot make the network polymer to become a linear polymer once you form the network polymer. Okay? Epoxy resin, phenolic resin, or silicone rubber, and these types of polymers are thermoset polymers. Whereas the polyethylene, or the polyamide, or PET, PVC could be usually a thermoplastic polymers. So you can process with the heat, whereas a thermoset cannot be reprocessed. Okay, so those were the difference between the network polymer and linear polymers. Let's say something more about the engineering plastics or engineering polymers, which is different from commodity polymers. Okay, we talked about the polyethylene, we talked about the PVC, okay, and the polypropylene and so on, which is very widely used right now in these days. The commodity plastics are the ones that we have just talked about: PP, polypropylene, polyethylene. Polyethylene has a high-density polyethylene and a low-density polyethylene. Okay? High-density polyethylene is called the HDPE, and low-density polyethylene is called the LDPE. Okay? We will, I think we can talk more about this in a little bit more. And this has a extremely low-density the polyethylene. PS is a polystyrene, just like a styropor, okay? Styropor or styropor. PVC is very widely used in our floor wallpapers, and the wraps. Okay, jjajangmyeon wraps are used. Is made of PVC wrap or polyethylene wrap. Whereas engineering plastics are the ones that is widely used, but it's much more expensive, okay? A little bit more expensive than the commodity plastics. ABS is very widely used in your mobile phone case or TV or the electronic parts, just like refrigerators. All those plastics which I just mentioned to you in the electronic parts, are made of ABS, mostly ABS plastic. ABS plastic is a top polymer made of 3 monomers. Okay? Acrylonitrile, butadiene, and styrene. Okay? Acrylonitrile is like acrylic fibers, so it's a crystalline. Butadiene is a rubbery polymer, so you can make a rubbery and network structure, which will give you a more flexibility. Styrene is a glassy polymer. Okay, styropor, the styrene is a glassy polymer, so you can make a very strong and tough plastic out of this top polymer. Butylene terephthalate, polycarbonate, nylon 6, PPO, polysulfone, and polyurethane are classified as engineering plastics. So we will anyway introduce to you and I will show you how we can make the polymers, but we sometimes classify this in terms of the quantity of the product or the price of the product sometimes. The commodity plastic or engineering plastics are the terms that could be used widely in the industry. Okay. Let's talk about the conformation and the configuration again. Okay? We knew that there are some difference between the conformation and configurations, right? So if I remind you, conformation is the one that could be changeable, just like a alpha helical structure or beta structure or gamma structure could be sort of exchangeable depending upon the solvents that you use, depending upon the environment that could be used, or gauche structure, stuff like that in your organic chemistry. So conformation is the one that is something related with the spatial rearrangements of your substituent groups so that it could be exchangeable. And depending upon your structural conformation, which is in the gauche or the anti-structure, you have a difference in the potential energy between these two conformations, but it could be exchangeable. Okay? Whereas configuration is the one that is a little different from the conformation, where you have usually you should have a double bonds. Okay? Like a cis and trans isomer. Cis isomer and the trans isomers are quite different. Okay? Quite different. It's two different molecules. So the maleic acid and fumaric acid are quite different, but you should have double bonds, and substituent groups are positioned in a different way. Okay? Like a cis isomer and a trans isomer, it looks very much the same, but has a different melting temperature, different property, and a different reactivity, and so on. Okay. So the configuration, one of the examples is the cis and trans isomer. It cannot be interconvertible. Okay. But in the case of the polymeric system, we have a little different isomeric system. Okay. What we call is a tacticity. Okay. Conformation or configuration will give you some idea of your low molecular components or organic components. But in the case of polymeric system, we have a different term, which is called a tacticity. For example, we have polypropylene or polystyrene or polyvinyl chloride, whatever you have. Those molecules that I have just mentioned to you has a very distinct structure with a carbon and carbon. Okay, you have a CC bond where you have three hydrogens. But you have the substituent groups, which could be, in the case of styrene, you have a benzene ring. In the case of vinyl chloride, you have a Cl, chlorine group. in the case of acrylonitrile, you have a CN group, okay, as I have just mentioned to you last time. So let's say this, red spot, red molecule is a substituent groups. Okay? Substituent group could be arranged in this way, which is in the same position, or it could be alternatively positioned, or could be randomly distributed, could be up and down. Okay? Depending upon the spatial arrangements, we have 3 different types of tacticity: isotactic, syntactic, or atactic. Now, isotactic and atactic are quite different, and it will be different in terms of the density. Density is the term that in the space you can pack how many molecules. Okay? In the case of isotactic, you have a quite linear polymeric system, so you can pack quite nicely. Whereas the random cases, because of the spaces that occupies this substituent group, we may have a little bit lower density in the case of atactic than syntactic or isotactic. Okay? So density is a very distinguishable property of this tactic polystyrene, so that tacticity affects the physical property of your final polymer. Okay? Atactic polymer is generally amorphous. Amorphous means that it doesn't have any crystallinity. Okay? In the case of polymer, we usually have an amorphous portion or random portion and crystalline portion. Crystallinity is always imparting from your linear packing. Okay? When the molecules are linearly packed, you can form the crystallinity. Okay? In the case of amorphous portion, we have a randomly distributed the chains in the space. Okay? So atactic polymer, because of the long and big molecules attached up and down and randomly in the space, it will become amorphous. So therefore, it's becoming quite soft because of no or very small crystallinity and flexible materials. Whereas isotactic and syntactic polymers are much more crystalline because of the high density. Okay? Therefore, it becomes very hard and less flexible. So even in the same chemical structure, which is a propylene, you can make an atactic polypropylene or isotactic polypropylene. Okay? Atactic polypropylene will be much more flexible film, okay? Flexible film, which covers your vinyl house. Okay? You don't need any hard material in the case of a vinyl house. So it's much more stretchable and flexible, which is made of the same polymer structure with the chemical structure in the case of the atactic polypropylene. But if you think about the film, which is very thin, okay, but in the supermarket or your, they will give you the very thin polypropylene film, okay, to carry your the watermelon, which is very heavy. Okay? Then those film from the supermarket could be made of isotactic polypropylene. Okay? It needs much more crystallinity. Okay? And melting points are a little different. Okay? Melting points are atactic polypropylene has low melting points, whereas isotactic polypropylene has a very high melting points. Okay, this means that you have a highly crystalline material in the case of isotactic than atactic polypropylene. Let's talk about the history of the polymers, okay? Which is the last part of the introduction to polymer cases. Well, polymer is history of the polymer could be back to the 16th century or 17th century. Okay? when the Europeans discovered the North America, usually the Spanish people went to Mexico, whereas Spain at the time, in the Middle Age, was a very strong country, but the UK, England, was not as strong as Spain at the time, but English people went to North America, okay? And they were very curious about Indians, American Indians, are playing with the rubber balls. Okay? In Europe, they do not have any rubbers. Okay? Rubber tree is always growing in a very hot, the weather, so that in Europe they didn't have any the rubber trees and rubber balls, and they were very curious about these rubber balls, whereas American Indians are playing around with the rubber balls, which will bounce very quickly. Okay? And this rubber ball was carried from Europeans in America, and when they went back to the Europe, then they discovered this the rubbers. Okay? But later, in the 19th century, early 19th century, Goodyear, Charles Goodyear. Okay? Have you heard about the Goodyear? Okay? This is one of the name of the company, Goodyear Tire Company, and he discovered how to cross-link these rubbers. Okay? This rubber tree is very flexible, but once they put the sulfur in the rubber and heat it up, it becomes insoluble. And that will make you a network structure, cross-linked structure. But at the time, they didn't know it was a cross-linked structure. But once heated up with the sulfur, then they cannot remelt to become a flexible state. Okay? Anyway, Goodyear started to make the pneumatic tire where we have wheels. Before this invention, they have hose, horseback trees, but because of this invention, they can even make an automobile. Okay? Automobile. So the invention of this pneumatic tire is a very strong at the time, and later, about 15 years later, the cotton was used, and celluloid was used as well. Celluloid is made from cellulose, and gun cotton is also made from cellulose, but cellulose was nitrated at the time. And anyway, the celluloid is a kind of plastic, and they will be used as billiard balls. Billiard ball is very strong, very hard material, and it was made at the time with the celluloid. Right now, I think this was made from the other cross-linked structure polymers, but not the cellulose, but a long time ago was made from celluloid. So that's the little bit of a history about the polymer in the 19th century and before. Okay. But later in the 20th century, excuse me. Okay, this is the latex material. Latex is the one that you have isoprene. And this is the starting monomer. What we call is the isoprene. Once you make the polymeric structure, then structure will look very much like this. Okay? you have two double bonds. So two double bonds will become forming 4 radicals. So the 2 radicals from this end will become forming the structure with the polymer, whereas the 2 radicals will form the double bonds in here. So double bonds in between this carbon number 2 and 3 will become a double bonds again. And this one will later, this is a linear polymer, by the way. Okay, you have a double bonds, but linear polymer, and it's flexible. However, if you put the sulfur in here, okay, sulfur will form cross-linked structure. And you have many of the other, this type of the radicals, and CH2 at the end will form and this is the linear polymer. Linear polymer can be cross-linked once you add the sulfur in here. And sulfur structure will become 2 radical. If you heat it up, you have 2 radicals. In between this long chain, the sulfur linkage can be formed in between these 2 radicals. This way, you can make the cross-linked structure with the rubber. You can mix the isoprene with the sulfur and heat it up. So what we call is a curing. Okay? Curing means that you make your material in a cross-linked structure. So that's the little bit of history about the rubber in the case of the pneumatic tire. But in the 20th century, Bakeland make the plastic. Okay? They didn't know what happened, but they didn't know about the chemistry at the time. But they know that once you make the cross-linked structure, once you add the sulfur in your rubber, then will not be meltable. Okay? Anyway, you can make a very elastic pneumatic tire. But in 1907, Leo Bakeland make the plastic. Okay? What they have done was that they put this phenol, okay? They put the phenol and add the formaldehyde. Okay, put the phenol and formaldehyde and heat it up. Phenol is a liquid around the room temperature, and formaldehyde could be water soluble. So it's a liquid phase around the room temperature, but once heated up above 100 degrees C, this material will become solid material. It's very hot, becomes plastic. Once it became plastic, it doesn't go back to your liquid phase. Anyway, what they have done was that, if you think about this, the 20th century, you have automobile, you have light, because of the invention from Edison he needs a bulb. He has a bulb, electric bulb, and there is a lot of advances in the communication, okay, because of the telephones and so on, and because of the electricity. If you go back to, if you see the plastic over there, you have the little bit of electrical insulation plastics. This electrical insulating plastic is made of this phenol, formaldehyde resin, okay? And they call this as a bakelite. They call this as a bakelite. Or they call this as a bakelite. Bakelite is made from bakeland, and it's a plastic. Anyway, this is very lightweight, cross-linkable, and it's very much like the insulating plastics, and was very widely used at the time. Because of this insulating plastic, there's a lot of advances in the industry. But they didn't know whether this is the polymer or not. They didn't know at the time how many molecules that was attached together. Anyway, they thought that phenol and formaldehydes are maybe forming a hydrogen bonding, so that they didn't know this was cross-linked structure at the time. But theoretically, there's a lot of questions. Okay, how can this polymer, how can this bakelite different from the phenol and formaldehyde? Okay? Phenol and formaldehyde was heated up, and it's irreversibly becoming a plastic, and it will not go back to the liquid phase. Were a lot of questions, but in 1927, there is a German, the chemist, Staudinger, raised the question, and he thought that maybe the phenol formaldehyde could have a high molecular weight. We know that this high molecular weight component, cross-linked structure or polymer, but at the time, the Chemical Society of Europe, or Germany, or Italy, all of those chemical society was occupied by the organic chemists. Organic chemists always know that the little bit of small molecules, but they didn't know about the large molecules at the time. Staudinger was trained as an organic chemist, but he thought that maybe molecular weight might be different from phenol and formaldehyde, which is very small. Of this bakelite. Bakelite may have a large molecule, and there is a sensation, okay? A lot of attacks from your organic chemist, but he thought that maybe this, you have a pretty large molecule from this, the phenol and formaldehyde, or maybe cellulose, or maybe rubbers, may have high molecules. This is what they call is a concept of the macromolecules. And later, about 30 years later, he won the Nobel Prize because of this concept. Okay? You all know this concept, but at the time was, very shocking and striking concept. Right after 1927, the concept of these macromolecules was suggested by the Professor Staudinger. There's a lot of, the inventions. The first invention was done by the chemist, the Carothers. And at the time, in 1929, he was assistant professor at Harvard University at the chemistry department. And he was very much concentrated on the condensation polymerizations. He wanted to prove this macromolecular concept suggested by the Staudinger in the case of neoprene, which is very similar to the isoprene, the polyesters and nylons. Okay. Polyesters and nylons were first made by the Professor Carrodus at the time, but in 1931, right after his publication in the Journal of American Chemical Society, back in 1929, he moved to DuPont company in Delaware, and he did a lot of work, industrial scaling up this polyesters and nylons. And in 1936, the DuPont successfully started to produce these polyesters and nylons. So when you remember your stocking, okay, big stockings in the first part of the slides, those are made of nylons in the 1950s. Okay. So nylons and polyester films or fibers were revolutionarily produced by the DuPont, but was first invented by the Professor Carrodus. Unfortunately, he did not receive the Nobel Prize because he suicided himself in 1935 in the lake of the DuPont company in Delaware. So the Professor Carrodus focused on the condensation polymers, and in Europe, many the organic chemists were concentrated on the addition polymers, double bonds containing the copolymers, whereas polyethylenes and polypropylenes. In 1929, the PVC, polyvinyl chloride, was plasticized. PVC has polyvinyl chloride has a chlorine group in the side chain. This chlorine group has 3 unshared electron pair. So those unshared electron pair, chlorine groups, gather together because of the dipole moments, and you will make a very strong material even in the linear polymers. So the plasticizer acts as something that will break your dipole moment between the chlorine groups. So once you add your aliphatic groups, then the chlorine group, the distance will be a little bit far away, and was because of the interruption of these chlorine dipole moments due to the presence of plasticizer. So plasticized the PVC could be fabricable to become a wallpapers right now, and the flooring 장판, floor mats could be processable because of the plasticized PVC. 1936, DuPont started to produce nylon, and the type of the polymers were produced back in the 1930s and 40s. Okay. 30s, you can see the invention of the Teflon by DuPont as well. Teflon coating, I think you all know about the Teflon, which is a coating material for your fry pan. And once you coat your Teflon with the on top of the fry pan, it will not, your egg will not stick into your the fry pans, and there's a lot of revolution in your kitchens. Even in your clothings, Gore-Tex fiber, Gore-Tex fiber is made from the sort of a Teflon coating on top of your fabric. Okay? Once you coat your Teflon coating, then the property will become very hydrophobic of your clothing, and so that the water droplet will not be smearing into your fabrics, so that it will just flow, whereas your wetted vapor from your sweat will go through. So water vapor will go through the Teflon coating or Gore-Tex fabric, whereas the water molecule, the water droplet will not go into. Okay? So this is the type of the material that you have seen. In the 1940s, there was a lot of invention about the rubber, the synthetic rubbers. Let's go back to, I guess, synthetic rubbers are very important in the 40s because you need a lot of pneumatic tire in the Second World War II. Okay? Pneumatic tires are usually made by the natural rubber and vulcanized rubber, as we have seen from the invention of the Goodyear in the 1830s. But because they need a lot of pneumatic tires, they started to synthesize these rubbers. So we called it as a synthetic rubber compared with the natural rubber. Okay? In Ohio Valley, they started to make the pneumatic tires from the synthetic the rubbers. And the rubber companies like Goodyear and Goodrich, those companies started to make the synthetic rubbers. And in 1950s, these two, the chemists, the Ziegler is a German chemist, and the Natta is the Italian chemist. They worked together about the catalyst to make the tactic polypropylenes. Okay. Before the invention of these two gentlemen, you can only make the atactic polypropylene. Or in the case of polyethylene, you can only make the LDPE, low-density polyethylene. Low-density polyethylene has branch polymer. You always have branch polymer because of the very high pressure in your reactor. They even, if you have the ethylene monomer, they put very high pressure up to 100 bar, 100 ATM. So you need the very thick wall of your reactor. And because of this very high pressure, you started to make the the branched chains. So you can only make the LDPE. But these two gentlemen introduced the catalyst. Okay, so once you introduce your catalyst in your reacting system, you can produce your polyethylene at low pressure, which means that you can make the linear polymers. Okay, once you make a linear polymer, then the crystallinity increases so that the density of your polymer is pretty high. That's what we call the high density polyethylene. Or in the case of polypropylene, you can rearrange them into the syndiotactic or isotactic polypropylenes. So because of this invention, you change your life, and they won the Nobel Prize about 10 years later. In 1960s, it started from the 1950s, but from DuPont, they tried to make the aromatic nylons. Nylon is a linear polymer, but it has aliphatic chains. Nylon 6,6 is made of adipic acid and hexamethylene diamine. Okay, adipic acid and hexamethylene diamine has a linear, aliphatic chain polymer, but in DuPont they were thinking about the linear polymer, which is made of aromatic rings. So they started to make the Kevlar and Nomax fiber, which is aromatic nylon. Okay? I think I have an example of Kevlar here. Okay, this is the Kevlar fiber. Little yellow, but it's not. It's very similar to the fabric they use, sir. But it's not, water. It's not it has a very high heat resistancy, And if you have any lighter, I think I will ignite this fiber. Usually, when you ignite your, the paper, it will, of course, burn immediately. But in this case, it's not burned, right? You may have a little bit of black ashes, but it's not burned. This is the example of the Kevlar, okay? Because of the aromatic rings, I think I will show you how we can make it, but because of the aromatic rings, it will not burn. And it will be used as a bulletproof, even the bulletproof, the fabrics or fibers. Okay? This white one is very similar to the Kevlar, but it has, this is made of aromatic ring, of course, but aromatic ring was connected in the para positions. So your amide group is positioned with the para positioned ones in aromatic rings. And this one is in the meta positioned, the nylons. The meta positioned one has a little color, and it will not burn as well because of the aromaticity. But it has less thermal resistance than this Kevlar fiber, right? So meta position one is, of course, has a heat resistance, but it's not as high as para positioned aromatic ring, which is Kevlar. Okay? Anyway, so Kevlar was very widely used right now. You can make a rope, okay? It's, the strength is very high, so that you can make a parachute rope, or you can make the, you can replace your steel, okay? Pipes and so on. In 1974, the polymer chemist, Paul J. Flory, received a Nobel Prize in 1974. And Paul J. Flory is not a synthetic organic chemist. He's a theoretician. Okay? His book, published in 1956, Polymer Chemistry, when he was a professor at Cornell University at the chemistry department, he published a book called the Polymer Chemistry. And this is the, at the time, in 1950s, he was thinking about many of the theoretical aspects of the polymers, including the Flory-Huygens temperature, universal constant, and others. Okay? And because of this, the theoretical aspect of this polymer, he won the Nobel Prize. And he visited in 1978 when I was a graduate student, and it was very nice to see him in person at the time. De Zong, he's the physicist in France, and he received the Nobel Prize as well in 1991 because of the leptation model, and he's also a physicist. Okay? In 2000, the scientists, Alan Heger, McDiarmid, and Japanese Shirakawa, won the Nobel Prize in 2000 because of the invention of the conducting polymer, electrical conducting polymer. Well, when I introduced you about the bakelite, I told you that the insulating plastics. Okay? Bakelite is insulating plastic, and up until the invention of this conductive polymer by these three gentlemen, the polymer is regarded as a non-conducting and insulating material to electricity. Okay? But in 2000, they received this Nobel Prize because of the breakthrough in the material property. What they have done was that actually the Shirakawa Shirakawa, and was working at Kyoto University in 1970s. And there was a Professor Byun, who's a Korean, was working with the Professor Shirakawa in Kyoto University, and they were working about the acetylene polymers. Acetylene, if you think about acetylene, you have a CH and triple bond and CH. Okay, this acetylene could be polymerized to become a double bond containing polymer, right? Double bond, alternating, double bond containing polymer. So when they make this polyacetylene and add the acid such as HCl or hydrogen chloride, then it started to become electrically conductive. And but this experiment was mistakenly conducted at the time, and they were not intending to make the conductive polymer at the time. Okay, but they could store this polyacetylene in various solvents, and this polyacetylene at the time was not soluble, so they mistakenly or just unintentionally they put this into the acid and started to become a little different polymer. Okay? Color changes, of course, and it was not reproducible at the time. So Shirakawa went to the UPenn, University of Pennsylvania, and these two gentlemen was the chemistry department professor, worked together, and Shirakawa was discussing with the polymer chemist, and they started to reproduce them, okay, because of these three. It was conducting polyacetylene, conducting the polymer concept was made in I think it was 1977, and they published this work. Okay, and later there was a big sensation, of course, at the time, because traditionally the polymer was regarded as an insulating material, but they invented the electrically conducting material at the time. And this polymer is widely used. Polyacetylene is widely used as a coating material in the outside of your most of the ships, okay, ships. Not because of the conductivity of this polyacetylene, but because of the other properties, which is quite resistant to the seawater, corrosion. Okay, corrosion-resistant coating, and also it could be used in actually electric conducting fiber. You can make a conducting fiber mixed with the polyester, okay, so that you can discharge your electricity generated from your body will be discharged. Okay? So usually, when they would like to make the dischargeable fibers, they used to spin the metal fiber and embed it into the synthetic fibers. But the metal fiber is difficult to make, of course, and it's heavy. So they started to make the conductive fiber and mixed with the normal the fibers to discharge your electricity. And also, the conductive polymer could be used as an outer coating of the stealth aircrafts as well. Okay? So it's a very important invention at the time. And of course, many of the other the researchers are receiving the Nobel Prize in the biomolecules and so on. So these are the little bit of history about the polymers and inventions. Okay. And let me just summarize what we have talked about. And traditionally, the polymer can be rubbery form, or the plastic form, or fiber forms. And those polymers are usually electrically insulating the material, but the thermally unstable. If you heat it up, it melts or it will be broken. But as you have seen, this Kevlar case or Nomax case, you can make a very highly thermal resistant polymer or high oxidation stable polymers. And this polymer can be used in aerospace applications or even very, the defense applications like a stealth. Engineering plastics are very important. Okay, I would say that this Kevlar fiber is an example of the engineering plastics as well. I think I will introduce the other fibers, such as the polybenzimidazole cases. This is also the fiber, which is a little dark brown color. It has a cross transition temperature of around 460 degrees C, and it could be used as interior material for the in the aerospace aircraft. I mean space shuttles. Okay? And you can make the block, the ceramic. You can mix it with the ceramic blocks in the case of the aerospace, and it's of course used as outer clothing of the firefighters, because they should be they should block the heat and so on. You can make a high strength aromatic fibers, just as we have seen here. You can make a non-flammable polymers, but you can also make the degradable polymers as well. It's not degradable. Kevlar fibers are not degradable, but there are some degradable polymers. Degradable in the environment, degradable in your body. Okay. Suture is a fiber. Suture was a fiber that will stick your, injured parts, okay? But long time ago, you need to go to the doctor again to take this suture out of your body. But right now, you don't need to, because this fiber is degradable inside your body, so that it will just smoothly go on. And many of the other types of polymers, like if you go to the plastic surgeons in Gangnam, they inject your some solutions, which is soluble and the degradable inside of your the face and bodies. So degradable polymers are very important in the controlled release of your drugs, agriculturals. Polymers are widely used in medical applications, just like what I have just said to you, degradable sutures and artificial organs, tissues, and even the conducting polymers. So polymers are very widely used so far, starting from your rubber pneumatic tires, and these days it's very important material at the time. So with that, I think I will close this session, but if you have any questions, please. Next time, I think we will talk about the quiz, but if you click this site, there are some questions about generally not the polymers, but about the organic chemistry. So please go on to the site and take some questions. Okay. We will talk about the chapter 2. So we will focus on the polymerization and degree of polymerizations and Caradus equation, because Caradus was a very important person, as I mentioned to you. So we will talk about how we can calculate the molecular weight and so on Friday. So please read about this chapter and introduction to the polymers. Okay? Okay, thank you, and I will see you on Friday morning.